All right, so let's go through a procedure to generate a general graph of a polynomial function. That is, we want to sketch the graph. I'm not looking for exact point-by-point plot of this function. I'm just interested in what is the general behavior of this graph. The actual point-by-point behavior of a function will have to wait until you're in calculus. But for our purposes, we do have the ability to get some sort of idea of what this graph is going to do because we know a little bit about the behavior of polynomial functions, these smooth continuous curves, and what they should do in the long term and at certain points where we know we can find zeros. So, to graph these polynomial functions, what we're going to do is we're going to examine the behavior from these particular perspectives. We want to determine the far left and right hand behavior first of all for this function. We're asked to graph, so what's going to happen to the far left and far right hand behavior? And in my example, I'm using the function p of x is equal to negative x cubed. I do want to be very careful here. Negative x cubed minus 3x squared plus x plus 3. And I'm already giving you the factored form right below it right here, but my leading coefficient, I know, my leading coefficient for this polynomial is equal to -1. And furthermore, I know that I have an odd degree. So if we go back to what we remember about our leading coefficients test, this tells us that this is going to be the kind of function that as x tends towards negative infinity, y tends towards positive infinity, and as x tends towards positive infinity, y tends towards negative infinity. Right? So this is our far left and right hand behavior. Right away, we know there must be at least one place where this graph passes through the x-axis, because if it's a smooth continuous curve, to get from positive infinity to negative infinity, it's got to cross the x-axis at least one place. The next step we should use, find our y-intercept. Well, y-intercepts are actually really, really easy to find, because all we're really looking to do to find a y-intercept is to find the value of the function at x equals 0. So if we look at this particular function and substitute in 0 for every value where we have x, we're going to find that p of 0 is equal to 3. In other words, this is a function that must pass through the x-axis, through the y-axis at the point 0, 3. So on our plot, we would go to the point 0, 3 and plot that point. How about the x-intercepts? Well, recall that we made the equivalence statements right here, that when we have the factored form, if we look at each of these factors, we could say that, for example, stand by, we could say, for example, that since we know that x plus 3 is a factor, that it's equivalent to stating that the point -3, 0 is an x-intercept. So in other words, this graph must be the kind of graph that passes the point -3, 0. We also know that x minus 1 is a factor. It implies that 1, 0 is an x-intercept. And if x plus 1 is a factor, then -1, 0 is an x-intercept. Well, what else could we tell? Well, we look at these points and we might be interested in going through and finding extra coordinate values to plot along with these points. So that's what I'm going to do right here. I'm just going to pick some points. After having chosen my x-intercepts at -3, 0, at -1, 0, and 1, 0, what I'm going to do is I'm going to determine the behavior of the graph near those x-intercepts by using my synthetic division. So I'm going to choose some values around the location of these x-intercepts here. And I'll choose negative 4. What happens at negative 4? Why negative 4? Well, negative 4 seems to be a nice number for the purposes of doing this problem. So let's substitute this in, and I'm going to find my y values by using synthetic division to get them for me. And I use this polynomial up here that has factors of negative 1, coefficients of negative 1, negative 3, 1, and positive 3. Carrying it out, carry down my negative 1, multiply, add down the column, multiply, add down the column, and then multiply again, and add down the column gives me positive 15. So I know that p of negative 4 is equal to positive 15, which is to say that I know this graph passes through the point negative 4, 15. And that's really, really useful to me because if I'm graphing this function, I know that I want to go to the point 4, negative 4, 15. All right, well, let's take a look at a couple other points right here. What about negative 2, right? That's between these two zeros. What happens there? Well, let's try it out. Let's put in negative 2, and my pen has stopped working with me. But at negative 2, I'll tell you that I know that if I worked it out the same way, I'm going to find that this graph passes through the point negative 3. And that what's more, if I take this graph and I checked out positive 2, I'm going to find negative 15 as a coordinate point, doing the same procedure, that is, using that synthetic division to figure out what my y value is that goes there. So what happens? Well, if I were to graph this function, right here using what I know, y equals negative x cubed let's see if I can evaluate this thing here a little bit more reasonably. Y equals negative x cubed minus 3x squared plus x plus 3. And plot it out, what would happen? Well, exactly what we predicted. The graph passes through all of these points, intercepts at negative 3, 0, negative 1, 0, and 1, 0, zooms off towards positive infinity as x goes to the left, zooms down towards negative infinity as x goes to the right, passes through the y-intercept at 0, 3, and our other predicted points as well. All right, good luck with your assignment, and I'll see you in class.